We continue today our forecasting lecture. With the use of filters. Yesterday, we saw how to use a filter to transform a data sequence that had some periodicity into a data sequence that appears to be noise. Here we applied differencing at lags 1 and 16. Because the noise that results from the filtering is easy to predict, we can obtain predictions of y if we know how to invert from x to y. And we have seen yesterday that for doing prediction at lag 1, then we can simply use this representation of the filter, which is in fact derived from the input-output representation of the inverse filter, of how we get x from y, and then I massaged it to put all the y's in the other directions, and we obtain that the prediction at lag 1 is given simply by this formula here. In this formula, remember, we're doing the prediction at time t. That means that we assume that yt minus 15, and yt minus 16 are known. What we will see now is how to go beyond this. For example, first step, how do we do prediction at lag 2? So again, we are at time t, and we want to say something about yt plus 2. Here I use the same formula of the filter, which is one of the many representations of the input-output formulas of the filter, and that's the one that allows me to compute y at time t plus 2, given x and given the previous y's here. Now, to do a prediction, we assume we know everything up to time t. So all the things that are this part here are in the past. So they are known. They are considered as non-random quantities. Yt plus 1, well, this is something in the future. If we want a point prediction which is equal to the expectation of what I'm doing, that's called a conditional expectation. Then the conditional expectation of the sum of things is the sum of conditional expectations. So what I need to do is a point forecast for this and a point forecast for that. For that, we did it already. We have computed the point forecast of t plus 1 at time t. This is what we had called y hat t of 1. The point forecast of xt plus 2, well, it's the same trick as before. It is the mean of xt plus 2, the unconditional expectation. And if we assume that 0 mean, it is simply 0, which gives this formula. We see that the point forecast at lag 2 is a function of the point forecast at lag 1 and the things that are known here. So this is again a recursive formula, but an easy one. I can do the same at every lag, and I will obtain this formula, starting from this formula here. And the method is simply from this formula, I replace the x by 0, because they're in the future, and they're replaced by the expectations. And from those terms, then I have to see which of those terms are in the future and which are in the present or past. Those that are in the present or past, I know their values, so there's no reason to forecast them. I use their values. Those that are in the future, I replace them by their forecasts here. For example, if I want to forecast what happens at lag 617 ahead of now, then I obtain this formula here. So this is how I did the computation to obtain the red forecasts that are given here in this curve. In general, we can do that in general terms. If I have derived data x that are filtered from y, I've applied a filter L, whatever the filter is. We had an example where L is the product of delta 1 and delta 16, but in general, the only thing I need is the impulse response of L. See, if I have the impulse response of L, that means I can write x as a linear combination of the y's with coefficients, the impulse response, and using the same trick, we can deduce that yt is given by xt minus the other terms of the impulse response here. I assume that the first term of the impulse response is 1, otherwise I can divide by 1. Divide by this term here. Since I constructed x from L, I can always construct an x such that the first coefficient is 1 This is not very important. This will give this formula here. Applying the same method as I've explained on this simple example, we obtain a point forecast done at time t at lag L as a function of the point forecasts of x, which are typically 0, or if the noise is non-zero mean, then it is simply the mean mu, and the point forecasts that are of the previous values, which are equal to the well, this is recursively by obtaining the point forecast of the previous values, as said. Now we have obtained the point forecast, right? The method is fairly simple. The trick is to use simply the representation derived from the impulse response of the filter L. In order to obtain the prediction intervals, we need to be a bit smarter, and here we will use the impulse response of L-1 here. Impulse response of L-1, that means how I derive Y from X. L is an invertible filter. Here, if it's the specific filter I had before, I can compute the inverse, and the inverse will give me formulas like this. So L was differencing at lag 1 and differencing at lag 16. The inverse of differencing will be integral filter. So that can be computed exactly, and we have this infinite formula. It's the sum of the 16 first terms plus 2 times the next 16 terms plus 3 times the next 16, etc. Well, this is the inverse response, the representation we have, but we will not use it. Right? This is a representation we could use to say, for example, if an alternative way of computing the point forecast. I could say the point forecast for t plus 1 done at time t. Well, I apply this formula here. If I assume x is 0 mean, this cancels, and the x are known, that would be exactly that. So that would be a formula that we can use, but it's not a good idea to use this formula because we compute x from y, then we revert. The other formula was directly based on x. And if L is exactly the differencing filter, we see that this is an infinite series with coefficients that grow. They don't grow exponentially fast. We're just at the boundary of stability, but L-1 is not a stable, a Weibull stable filter. It's not a very unstable one. It grows mildly, but still, it's not a good idea to use this formula. That might lead to floating point problems. However, it's a good idea to use it in a theoretical way to obtain prediction intervals using this trick here. If I rewrite this formula and I do it at time t for lag 3, so I write y of t plus 3, so I write the formula at time t plus 3, and then I specialize all the elements of this formula that are valid at time t here. Now, if I reason, again, like I said before, I want to compute the conditional expectation of yt plus 3 given all the past and present up to time t. This will be set to 0. So, and this will be equal to themselves because they are known. I know xt, etc. In other words, all this red bubble here is exactly the forecast I can do at time t for yt plus 3. So it is y hat of t plus 3. We have obtained y hat of t of 3 with another formula, but this is another representation of the same quantity. Why am I saying that? Well, because that gives me this formula here. I can say that the value, the exact random value of t plus 3 is equal to this, the sum of the filtered terms, which are random and unknown at time t, plus this, which is known at time 3, at time t. This has a name, it's called the innovation formula. It is the innovation because this is saying that how the future, yt plus 3, depends on what we know now, which is yt hat of 3, plus all the future things that are not known now that are called the innovation. So it explains how the innovation is added to what we have now. So it's not the formula of the filters we had before, it's one that is derived from this thing here. And this is the basis for computing prediction intervals, because now, if I condition upon the past up to and including the present of time t, then we see that The future thing is given by random things plus something that is known here. So the distribution of the future, conditional to knowing everything up to time t, is simply a constant plus the convolute or the distribution of the sum of those three innovation terms. In the model I've done here, in one of the versions of this model, I'm assuming the noise terms, the filtered noise terms, are IID Gaussian with 0 mean and sigma square variance here. Therefore, I know what is the distribution of this. This is the sum of three independent Gaussian variables. So it is also Gaussian, with a mean that's the sum of the mean and a variance that's the sum of the variances. So it's a noise term with mean 0 and variance 3 times sigma squared, which in other terms can be expressed as saying the distribution of yt plus 3, given the path up to time t, is Gaussian, with a mean this quantity, yt hat of 3, and variance 3 sigma square. How would you translate this into a prediction interval? So it's your turn. I close the poll in a few seconds. 100% correct answer. Of course, since the distribution is Gaussian with mean this and variance 3 sigma square, so with probability 95%, we are between plus and minus 196, square root of the variance, which is square root 3 sigma. So with this formula, we see how to obtain prediction interval, which is what I did on this example here, and I obtained the dotted lines that are presented here. That gives me the prediction intervals using this method. This method was assuming that the filtered terms is this noise is white noise, IID Gaussian with mean 0 and variance sigma square. Perhaps this assumption is not the optimal one because, as we see, the prediction interval are very large. But nonetheless, that gives us in general a formula. If I have filtered y, I've obtained x, and x can be assumed IID Gaussian. Then in order to obtain prediction interval, I will redo what I've done exactly before. What I need is now the impulse response of the inverse filter. And when I do prediction at lag L, I take the first L terms of the impulse response, and I obtain this formula. This quantity will take the sum of the square of the coefficients times sigma square, and that will give exactly this prediction interval. So as you see, once we have filtered the data, coming back one way or the other is easy to obtain. If we obtain the good representation of the filter for obtaining the point prediction, it's a good idea to use the impulse response of the direct filter to obtain the prediction interval. It's a good idea to use the impulse response of the inverse filter. In either case, computing the impulse response is required only for the first terms of the impulse response. We don't need the entire impulse response. In particular, it's easily computed by all kinds of tools, including MATLAB. Here is a comparison of the two methods we have seen so far. This is the method of last week. We have a linear regression model on a sine wave that gives us a good prediction. But the point prediction is perhaps obviously too smooth. It doesn't correspond to reality, but the prediction intervals are good. Here is the other way around. The point predictions are better. They follow better the irregularity that has been observed in the data, so they capture it better. But the prediction intervals are too large, probably. Capturing the point prediction well is something we would like to keep, so we'd like now to fix the prediction interval. Observe a major difference between those two methods. Here, I needed to estimate not just the noise term to obtain the width of the prediction interval, but also the parameters of the linear regression model, the coefficients of the sine and cosine. Here, I did not need to estimate anything. There is no estimation. I simply applied a filter. The only guess I did is that applying the filter at lag 16 was a good idea, which is similar to the guess I did on the left. Here, I needed to assume that the period 16 was okay to propose a sine wave with period 16. But here I needed to estimate the coefficients of the sine. Here, there is no coefficient in the filter or anywhere to be estimated. So the second method is more parsimonious, so has more chances of working better because we estimate fewer things here. What we will see now is how we can handle cases like this one, where obviously our assumption that the filtered data, which is this one, is IID Gaussian is not good. Not Gaussian probably because there are large differences, and IID also probably not good, as we will see, because there are probably correlations between the noise terms. Those correlations may exist in the data. Quasi all data have internal correlation. When doing filters, when applying filters, we might also introduce correlation because the filter introduced the data again and again. So together with filtering the data, typically we want also to handle correlations with noise. And this is done with the same techniques using filters. In order to see whether we need to embark into this, we need techniques to decide whether a sequence is IID. So the first thing to look is, does it look stationary? This is typically done by out-of-band inspection of the data. For example, one of the data series we've seen has obvious periodicity. So if it's periodic, it's not stationary. Remember that stationary means that the process is stationary if, by observing the process over a window of time, I have no idea, or two windows of time, one that is young corresponds to small times, another one which is old corresponds to large times, two windows of the same size, it's impossible to say which of the two is the young, which of the two is the old window. Here, if a process has a period, then it's obviously not true, because if I observe the process at night, I take a window of observation that is at night, another one that is during the day, then obviously a machine learning technique will be able to infer which one is the day, which one is the night. So a periodic process, or a process that is random but has some periodic component, violates the stationary assumption. And one way to get rid of it is to filter out the periodicity, as we have seen, by using the Roberts filter or a differencing filter at lag S. So we assume it's stationary. Same thing for growth. If your data is expanding, is getting bigger and bigger, then differencing it once or several times will remove the growth, and then it's a candidate to be a stationary process. But is it IID? Then to be sure, one thing is to use tests that are based on the sample autocovariance function. An autocovariance function will not tell you really whether it's IID, but something that is IID will have zero autocovariance except at lag 0. So the autocovariance is given by this formula here. For example, there are variants of the formula. Sometimes you rescale by 1 over t. This is essentially capturing in signal processing the autocorrelation of the function. In statistical term, the autocorrelation is typically called the estimate of this rescale by gamma 0. Gamma 0 is an estimate of the variance if we rescale by 1 over the number of data sample. So this is what statisticians call the autocorrelation function. And if the process is truly IID, then the theoretical value of the autocorrelation are 0, except for every t except 0. Now, in reality, we don't have the theoretical value, but only an estimate from the data. But there is a theory that says that if your data sample is large, if your sequence is IID, then a 95 confidence interval for the autocorrelation estimates here is given by this 196 over square root of n, which is used either in visual tests, or in formal tests. We'll talk about tests in the coming module. Here in practice, that means I can estimate my autocorrelation function. I did it here twice. I did it for the process y of t, here, the original data. I computed the autocorrelation function. This is what I obtained. You see here that this is obviously not a stationary process, but that was obvious from the beginning because of the period, and the period is visible in the autocorrelation function. In fact, there was a question yesterday on the chat, how do we estimate the period if we don't know it? Well, the first step of estimating the period is to take the sample autocorrelation function and then do a discrete Fourier transform to find the peaks of the correlation. That will give you typically the period here. So here we probably don't need a discrete Fourier transform. The peaks of the autocorrelation function already, the distance between the peaks will give us exactly the period. So obviously we don't want to examine YT, it's not a candidate to be ID, but if we apply this to the filtered data, we obtain those coefficients here. So we see that most coefficients are very small, except the coefficient at small order. In particular, there's a big one. This is at lag 1. That's normal. The first coefficient is always 1 by definition. It's gamma 0 over gamma 0. And then there's a few coefficients that are large, and the coefficient at lag 16, which is large here. And to know what large means, it's based on putting these confidence intervals, which are plus or minus 196 over square root of n, where n is the size of the data sample. So MATLAB plots, when you ask them to plot an autocorrelation function, if you use one of the options, will automatically plot those values. So here we see that many values are very small, except the first ones here, which indicate that there is correlation. In fact, there is a strong negative correlation at lag 16, which means that the data has negative correlation from one day to the next. If there's a lot of traffic today, there will be a lot less than usual tomorrow, and vice versa. This is how things are in this time series. And we see also that there is residual autocorrelation, which is not huge, but is not negligible here. So it's not ID. This test will say this is not ID. So how do we do when it's not ID? Then we model it with something that is a process that has ID correlation, which is called an ARMA process. Or another way to put it is we will filter the data with an ARMA filter until the filtered data appears to be ID. That leads to the concept of ARMA process. An ARMA process is defined by this. So a stochastic process, xt, is derived from a white noise process, epsilon t, which is in the literature on ARMA process is almost always Gaussian. So here I'm assuming it's ID Gaussian with same variance, so the homoscedastic assumption. From epsilon, I derive x at time t using these equations here, which you recognize is the filter equations. On the left, we have a denominator filter. On the right, we have a numerator filter. And here, you also need the usual convention. What happens for indices that are out of bound here? And this is a zero mean ARMA process. Now, if you want a more general ARMA process, you say that given a number mu, X is an ARMA process with mean mu if xt minus mu satisfies this. So you apply this equation where every X is replied by X minus mu. Here we assume that the filter that's defined here and its inverse are both stable. If I want to write that in a more compact form, using what we saw yesterday, if I call F the ARMA filter, in operator notation, I can write it in this way. Here we have the denominator, here the numerator. The denominator, as usual, I have leading coefficient 1. The numerator, I usually will also take leading coefficient y. The reason is that because I multiply this with epsilon, I can always change the variance of epsilon if I want to change this coefficient. So both the variance of epsilon and the first coefficients can compensate each other. So the system is undetermined if I don't impose 1, but this is not a convention that's not always used. The important thing is that if we ignore mu, the constant, the formula we had before, we're simply saying that x is equal to f epsilon, right? This formula is here. They say that if I take as input sequence epsilon and output x, these are exactly the equations of an arma filter, which is this thing here. Now, if I have a non-zero mean, that means x is equal to a constant plus this notation. So this notation is an object-oriented notation. You have to be careful what it means. So here mu is a constant, f is a filter, so an operator on sequences, and epsilon is a sequence, and x is a sequence. So adding a constant to a sequence means we add the constant to every term of the sequence here. So an ARMA process is simply one that is derived from a white noise process by an ARMA filter, plus possibly adding a noise, a non-zero mean. Here are three examples of trajectories of ARMA processes. For each of the process, I've written the equations here. So you see the denominator terms, the numerator terms. So this is a generic ARMA process. Now, if the filter is an autoregressive filter, that means if the numerator is reduced to only one, then we obtain this. So that's an autoregressive model that's very often used. It says the value of the process at time t depends on an innovation, a noise term, plus also a regression on the previous values here. This is also why it's called autoregressive. And a moving average is when the denominator polynomial is trivial. That means here the process is an average of innovation term of noise terms here. Here I'm showing three samples. Well, we see things here. So those are white noise. So those are zero mean processes. So they are noise, X are noise processes. But as we see, there is a correlation. For example, we see here that X tends to show some patterns here. There's like a pseudo period. It's almost like a sine wave, but oscillating plus or minus this. So there is negative correlation at lag one, obviously, but there is also some correlation. Once you start increasing in absolute value, then you will continue until you change your mind. But this is not the fact that a number of values the absolute values are decreasing appears to be a trend. So there are local trends, which is what exactly we would like to model. An important thing to remember, all those processes, as we will see in a second, are stationary. So that means that this quasi-period thing here, it looks like a sine wave, which is oscillating with a second envelope here. But this is purely random. The fact that it happens here is purely random. It might happen somewhere else. So if I do another sample, if I look at this part of the sample I have not seen here, so here that's a process that will have a tendency to show such big oscillations, but when they come, is completely unpredictable. So that is our toolbox of ARMA processes here. Which of these MATLAB scripts would produce a sample of an ARMA process? I close the poll in a few seconds. And the correct answer is both. In fact, in order to be a valid ARMA process, we need to apply an ARMA filter to a noise sequence. Rand n is the noise sequence. This is an ARMA filter. But we need also to verify that the filter and its inverse are stable. So here we can see that the polynomial, numerator polynomial is z minus 0,4. So the root is 0,4. Here the root is minus 0,4. So both roots have modulo less than 1. So the filter is stable, and its inverse, which by the way is the filter used here, the same applies. It is stable. So both, so the denominator of both has zeros that are modulo less than 1. So both filter and reverse are stable. So A is an ARMA process, and of course B also, because the conditions are the same for both. A few things about ARMA processes. An ARMA process is an example of a Markov process, but a Markov process on infinite continuous state space, which is a bit complicated. But here there are easy things we can say. First, it's a Gaussian process because xt, if we use the impulse response of the ARMA filter, we'll see that at time t, xt is given by a linear combination of epsilon. So at least at every time t, x is a Gaussian random variable. And in general, the process can be qualified Gaussian. Now we are interested in, for example, what is the covariance structure of this process. And it can easily be computed from this. And we obtain a formula like this one. We would like to see in particular whether an ARMA process is stationary, because we are modeling noise that is assumed to be stationary. So if the process is not stationary, then it's embarrassing. And now the answer is a bit contorted. First, to know whether it's stationary for a Gaussian process, the only thing that is required is to see whether the mean is independent of time, which is true here, and whether the covariance is independent of the time at which it's computed. Of course, it depends on the lag. If I compute the covariance of xt and xt plus s at time t, if it depends on t, then it's a non-stationarity property. So it should not depend on t here. In reality, it does depend on t, because we find this formula here that can be obtained directly from this. But in practice, when t is large, and if the filter is stable, and if we take ARMA filters that are stable, as we should do, then the decay will be exponentially fast. So this series here is very quickly, for t large enough, independent of t, because it's close to the infinite time series that we obtain here. So we find something that is as expected. For if we take Markov process, we know if we simulate a queue like you're doing in the lab now, when you simulate a queue, it is not strictly stationary. It depends on your initial condition. So the same is true here for an ARMA process. If I look at the process with t small enough, then it will not be necessarily stationary. It depends where I start. And with my convention, I start with xt 0. So this zero initial conditions affect the process. But if t is large, then it becomes stationary, and the covariance, for example, is given by formulas like this. So I give references here to see if you want to do a more sophisticated analysis. But the take-home message is that an ARMA process, with this assumption that the filter is stable, will give a stationary process. In particular, if we apply the formula for the variance of the process at time t, we will find this thing here, sigma square times the infinite sequence of the square of the impulse response of the ARMA filter here. Now, the first coefficient is typically 1. So that means that the variance of xt is larger than the variance of the epsilon. Well, that's an important feature, and that is exactly what we would like to do. We have noise terms, xt. If we assume the noise term is IID, then we will have that all the h are 0 except the first, and then the variance of xt xt is an epsilon, and its variance is sigma square. So sigma square quantifies how much uncertainty there is in my time series here. And if we say it's IID, we mean every term contains the whole uncertainty. But when there is correlation in the noise, it means that the uncertainty that there is in the noise, sigma square, is less than the variability of every noise term. This is where, if we model the noise terms as IID, then we exaggerate the uncertainty, and therefore we expect to find prediction intervals that will be pessimistic, that will be too large. How do we know which process we should use? Well, there are those classical observations that are based on the correlation function. Here is the correlation function of the theoretical process, not the sample autocorrelation like we've seen before. If I have this process here, in theory, I can compute using the formulas we just saw. I can compute the autocorrelation, and MATLAB will do it for us, and I obtain this. There's a variance of autocorrelation, which is called partial autocorrelation, that I will not discuss in detail. And they decay very fast. And now there are subtle differences, like, for example, if I have an autoregressive process versus a moving average process, the autocorrelation of a moving average process is exactly zero after some lag. Why is that? Well, because a moving average is an average, for example, here of 3 epsilons. If I take the average of 3 epsilons, then if I move in the future and I take the average of other far away in the future, then the 3 epsilons I'm taking in the future are not overlapping with the 3 epsilons I've taken now. Since the epsilons are independent, then those two parts are non-correlated. So the correlation of xt in this example and xt plus 3 is 0. So xt plus 3 is independent of xt here. So this is visible here. Now, there is also the partial correlation that has the converse property for autoregressive systems. The partial correlation indicates how much residual correlation there is from xt to xt plus 3, for example, when we ignore the dependency on xt plus 3 that comes from the intermediate terms. Here, there is correlation all the way, but we see that xt depends, for example, on the past by the intermediate values. So if we condition upon the intermediate values and we look how much residual uncertainty is there, that is captured by this function here. Take home message: if you have a process, you analyze its sample autocorrelation, and if it looks like the values after some term are 0, then a moving average is a good model. If for the partial correlation is the same after some lag, then an autoregressive model is okay. And if none of them, then you will have to take a full ARMA process. In the literature, and very often, we will find the concept of arma process with the I. Well, this is nothing else than what we have done here when we, from the initial time series, we apply a differencing filter, like we did before. Then if we model the X that we have obtained with an ARMA process, then the Y is called ARIMA. I stands for integrated. We have differenced here, therefore, for get back I, Y, we integrate here. And this is the general classical method for fitting time series. We first apply differencing filters, justify as we said before. The resulting noise term we obtain will be modeled as an ARMA process, and therefore the initial process is called ARIMA process. In reality, we will not need ARIMA other than knowing what it is. In reality, what we need to do is to be able to apply the filters like we did here. How do we do that in practice? We have seen here that my Y time series, finding the L was very easy. I looked at the period, I found the period 16. I also saw that there is a very small trend, increase in trend, so I apply differencing at lag 1 and 16. If I would have, after doing that, I see that my time series still increases, then I would perhaps apply another differencing filter. So after that, I obtain X. And now the question is, how do I obtain the ARMA model for X here? Well, the key thing is first to check the ACFR residuals. Now, how do we fit the difference process when we use a procedure? Which procedure? Well, maximum likelihood optimization estimation. But it's a bit tricky, so we'll not see in detail how it's done. This is not a convex problem like all the problems we've seen before. It's a least square problem if we assume Gaussian noise, but a non-convex least square problem. So there is no closed form or even not an algorithm. It's guaranteed to obtain the maximum likelihood estimation, but there is heuristic algorithms that are iterative and in general, or so far, has been proven to be very good. But this, because we are solving a nonlinear optimization problem, as you might know from other experience you have, optimizing something when you do a non-convex optimizer requires usually an initial guess. So we would use things like gradient descent, for example, but we need an initial guess. This is why typically this ARMA process filtering will try to first do an estimation that's easy. Something that's easy to fit is autoregressive model. Why is it easy to do? Because for an autoregressive model, we can compute easily the autocovariance function. Same thing for moving average. And one method of fitting consists in one, estimating the sample autocorrelation function of the process, of the X process, and then solve a nonlinear set of equations, find the coefficients of the autoregressive filter that would give the same autocovariance function here. Of course, this itself is iterative, but this is fairly easy to do if we assume an autoregressive or a moving average model is easy. So this is why, in general, the fitting will be done in two steps. First, fit an autoregressive model. Then use this autoregressive model as a first step of your maximum likelihood estimator. So in other words, you set the moving average polynomial to 0, but you keep the autoregressive coefficients, and then you run the estimation, the optimization procedure. Once you've done the fitting procedure, MATLAB, for example, does it with Rmax, then it's a good practice to check the residuals. Now we know what the residuals are. If you remember this innovation formula we have seen for forecasting, we know that the forecast done at time t-1 at lag 1 is equal to xt. Sorry, xt is equal to the forecast plus the noise term epsilon t, because the first coefficient is assumed to be one of the filters I have. So that gives us a way to understand the forecast, but it also gives us a way to estimate the noise terms here. So for all of these processes, the noise terms is given also by the innovation formula. And as we have done in the previous cases, once we can estimate the residuals, we can check whether our fitting is okay. How do I do that? Well, by looking for the ACF and see whether they have 0 residuals. For example, for the time series we have seen so far, here is the autocorrelation function we find for the X values after applying differencing at lag 1 and 16. So I will ask MATLAB to fit a model to this thing here. Since there seems to be autocorrelation up to lag 16 and more, I need an autocorrelation coefficient that perhaps sorry, I applied this fitting method, and I observed that many coefficients are non-zero, which is embarrassing, right? It means I have perhaps an overfitting problem. We've seen that we need to be careful not to have too large number of parameters. Of course, when I do this, and Rmax will do it for me, I will compute also the, for example, AKK information criterion, which we have seen depends on the log likelihood of the estimated model, which itself depends only on the log of the residual mean square error. So MATLAB will return all of this for us. So I can compute a model order, which is the number of coefficients I have for the both moving average and autoregressive polynomials. That minimizes the AKK information criteria. To do even better, if I find that a large number of coefficients are small, I can force them to be 0 and see whether the fit becomes equally good, which in many cases will be the case. So I did that. I applied the best AKK information criterion filter to this noise term, and so this is the residuals I obtained after that. And here is the autocorrelation function of the residuals. So we went from this with large autocorrelation at like 16 and non-zero autocorrelation all around between 0 to 32 to this here. So here the y-axis scale is very different now, of course. We see that our fit is not perfect. There are still some autocorrelations that are above, but it seems okay because those are 95% confidence interval. So it's okay to have 5% of 100 points that are above, which is more or less what we have here. So we have a fit here that is reasonably good. And here is the prediction interval I obtain. How do I obtain the prediction? Well, we've seen how to do the prediction once the data is filtered. So here I had X before. So in the beginning of this lecture, if I do just the time differencing filter, I obtain the X time series. From a prediction of X, that was trivial to do, I obtain a prediction of Y. This is what we obtain. We obtain the point forecast in red, and in dotted red, the prediction intervals. Well, exactly the same method is applied once I have modeled X as an ARMA process, because modeling X as an ARMA process means I filter one more step in order to get epsilon. And therefore, Y is equal to L minus 1F epsilon. So what I did from X to Y, I can do equally well from epsilon to Y. I know how to predict the epsilon. Now they are reasonably IID, so my prediction method I did before seems to be reasonable, and the methods are the same. An impulse response of L1 minus L minus 1F will give me point predictions, and the impulse response of the inverse filter will give me the prediction intervals. And this is what I obtain with this method. So we see two things. First, the point predictions are a bit different. They appear to be better. In fact, even the point predictions are modified a bit better. And also the prediction intervals are constantly smaller. So the job is, mission is accomplished by modeling, going one step into the noise and trying to apply relatively simple filters, ARMA filters. I could dramatically improve my prediction, at least if I care about the prediction interval. Voila, that's all we will do for today. We still have a few words to say about forecasting and the use of other methods. We will do that at the next lecture. The next lecture will be after the Easter break. So the quiz also is broken into two parts. There is a first quiz on forecasting, which is now, and the second part of the quiz of forecasting, which will be the following quiz, will be on the lecture of today and of next lecture. In the meantime, I wish all of you a very good Easter break. Take advantage of the break to stop working at least for a few days. And if you stop working, you will meet friends and family. Don't forget to do a test. Before that, you know that they are now free in Switzerland, and you can do as many as you want. Bye-bye.